I please request Mr. Holger Schuh, Senior Manager, Thermal Technologies, Equipment Partners, Henkel, will be enlightening us with the details on development of innovative material, testing methodology, and simulation model for safe battery systems. Over to you, Mr. Schuh.
Thank you. So, yeah, thanks for the introduction. I think my slide deck is still loading to the computer. Happy to be here. I'm not introducing Henkel in more details. We have a large booth. When you exit here, go towards the right, we showcase all our different products. I want to highlight a topic about battery safety today, which I think is of super interest for all the designers. So we had a very specific motivation. Why we are doing this presentation is actually we see in the path forward of all kind of different battery designs a massive dynamic. Yeah? So we're running almost after every design on every OEM and try to follow up. Making those thermal management materials and fire protective materials, we're actually aiming to be more proactive as a chemical company and not only reacting to specifications. So what we like to do is actually developing our own test systematic to see how our materials not only perform in rudimentary testing, but really in a battery-like system, so closer to be in a realistic situation. And what is also super important for us is we always validate our materials if they are working in a process. Yeah? So we are not only developing materials and give it to the customers and then tell them to have fun and test them by themselves. So for us is the process a big relevant topic. And then also what is super important for us is the future trends and regulations. Yeah? There's no global alignment for battery safety at all. So we try to catch up and stay tuned with our teams to the different governments and follow all those regulations and make sure our materials fulfill them. Yeah? So I quickly go through the battery requirements, how we see they change over the time, telling a little how we tackle this thermal runaway topic and how we develop, and even more important, how we test those materials in our house. And then about thermal management, which is a second big contributor to battery safety, how we develop those materials. So we did a significant change in how we formulate that material, show you how we enabled process technology on the two material categories, and then of course I'm open for your questions. So as mentioned, thermal management technology and propagation prevention materials are a significant contributor to battery safety. Of course, all those materials should also contribute to range and performance. Everything in battery is about system cost, so they also should not be super expensive. And then a key topic in battery design is also how we integrate those materials inside a battery. So here you see different designs actually. So you have a modular scope here with pouch cells built into what we call a shoebox. Then a design which is very common as of today is this modular battery pack. So you build everything into modules and the modules go into the battery pack. But what you're probably familiar with, we all talk most recently about the cell-to-pack design. So everything is getting rid of mechanical parts simply to reduce complexity, weight and height, of course also cost, and then, also enlarge the energy density and driving range in a car. Yeah? So those are all the changes we see. And how do we test now those thermal propagation materials? You're probably familiar with the topic thermal runaway here and its propagation. So you could have different types of impacts to a cell, either mechanically, electrically, or thermal, which brings the one cell into a so-called thermal runaways. Worst case, the cell, no matter what type of cell, then catching fire. And then if you're not taking serious actions inside your battery systematic, then you have what we call a thermal propagation. So the event cascading through the battery, and saying that we have different types of materials at different interfaces which delay this event more or less. So we're looking into two different areas. So one is actually protecting the battery from the outside. So grass fire tests are in place. So we have different materials, coatings to protect the housing on the inside or even on the outside. We have different pottings and sheet material really to protect the battery from outside. But we also have, what is super important, the fact that we also have protect the passengers. Yeah? So there are different guidelines. You might be familiar with the China regulations. So we have to take care that if in an event of a thermal runaway or a propagation inside the battery, the passengers in the car are protected over a certain amount of time. That's super important. We will not, with our materials, make sure that it's not happening. It will happen, and if it happens over a longer time, also our material will fail. So we really delay this event and make sure that the passengers could evacuate the car in a decent amount of time. So how are we approaching this to be more proactive, as I mentioned? We simulate cell abuses and thermal runaway situations already on the computer. Yeah, so we do not want to waste time and material, resources and energies. So we have the capability and ability with software tools to simulate and trigger thermal runaway situations already at cell level. Then we go into a propagation event and simulate and see how a material performs, and then also go outside the entire battery pack and evaluate the heat dissipation here. What we do and how does this look like? We're building models on the computer with the different interfaces. So we have different types of potting, we have coating materials, and what we do is actually, with these models, we bring in all different types of materials and change the characteristic of the model, and immediately at the computer see the impact to the event. Yeah? If we go to different thermal conductivity values or heat capacity values, heat resistance values, for example, on a potting material, then we immediately have an output on the computer. So we are not burning batteries for nothing. We really see the impact. We could also play with chemistries and different filler types and see if even the application, the way how we build everything together, makes a difference in how the battery behaves in a thermal event. Yeah? And then, of course, the form factors, the packing efficiency, that's something we also could simulate and bring together. How we test this, so simulation is one, but the other side is really validate what you simulate. So we have partnered up with the PEM in Aachen. It's a well-respected institute where we could do those tests, of course. So this is how we started with our thermal materials and our propagation prevention materials. So basically we started with a so-called open flame test. So we simply put the coatings and the materials into an impact with an open flame with 1100 degrees centigrade. We also went further to what we call a particle shooting test. So if the cell is bursting, we also shoot on the coatings, for example, those particles and see what happens. And then we did a thermal runaway case. Everything more open, yeah, really not close to a battery design, and here just with one cell. What we're looking into is designing new tests which are more realistic, really mini batteries, which is easy to build and assembly together, and see what really goes on inside a battery. So here's some tests. So you see on the left side, that's the open flame test on a coating. Yeah, it's just an impact of temperature. And on the right side here, you see the particle shooting test. Yeah, so we have a vertical oriented lid, simulating the battery lid, and then we shoot it with particles. Everything is open, so we do not really have a direct impact. The energy could burst away also, so it's a little off from the realistic situation. And that's why we're going for those real abuse tests here on the thermal propagation prevention materials. And this is then how it looks like. So we have more control on the exothermic reaction. We integrate everything more in a safe testing environment. We could actually tweak the smart venting situation. We have a cell-to-cell and even modular scope, so we get simply larger, as I mentioned, closer to a realistic battery system, and also have optimized sensor positioning and could tweak the design, as mentioned, closer to the real situation in a battery. And that's how it looks like in the PEM. So Henkel is not able to do those tests in-house. Yeah, we're dealing with chemicals, so we are not burning batteries, and next door we do something with chemicals. That's way too dangerous. So that's actually this new system what we do here. And you have, we initiate actually one cell and see what happens with our material. Yeah? And that's all on smaller scale, of course. It's not a real battery. We also could build batteries in there at the PEM and really burn an entire battery, but that would simply be too costly. But we get already good data out of those testing, what happens with our material and what's the impact. Yeah? So coming from the simulation towards a validation small scale with this open test and protection, we go to a more realistic test here. What we do on thermal management has also significantly changed to be more reactive to the market. And I like to show you quickly what is a thermal interface material. I'm not sure if everybody knows, but the aim of a thermal material in a battery is actually to transfer heat from a heat source through the entire material to a cooling plate, for example. Yeah? So it contributes significant to keep the battery in its thermal comfort zone. It's very important. Yeah? And here you see that's a modular systematic, so you have the battery stack built into a module. Here is what we call a gap filler material, and then the heat goes during the fast charging events from the cells through the module housing, through our material into the cooling. Yeah? So that's what a thermal material is doing. By nature, we put in what we call ceramical fillers to make the material thermal conductive, and to build such material needs formulation, so you mix everything together. What we started is actually, we formulate the materials no longer in our lab, we formulate it on the computer. So we have fillers and different resins, and on the computer, a chemist builds the formulation. So we run 100 different formulations a day, and then we pick the best out of it by thermal and mechanical characteristic, and then we go further. So we probably run 1,000 formulations before we even touch a real formulation. So we save significantly time, of course resources, we are not wasting raw materials, and also energy because we simply do not mix. Yeah? That's the first approach we do. Then of course we do a significant market screening to build platforms. So we are not reacting more to a specification. We have formulation 60–70% ready to go, and then by the design from our customer, we tweak those almost ready formulations. Then what also happens is that, because processing is super important, when a PD engineer at our lab has a formulation ready, he could go one floor down, go it on a real life dispensing equipment and run it through a serious equipment. So we see already within a few days if the formulation is in scope and also fulfills the requirements in processing. So it's a continuous cycling, evaluating, and learning in our labs. Yeah? So that's really a change in how we do this. We also changed our scope, how we test the material. We went away from test to pass towards a test to fail. So we want to continually stress our material till or until they fail to understand what was the reason and what was the root cause and what was the main driver. So we could even bring in smaller batteries into environmental shakers. So we could run all kinds of environmental conditions by also shaking mechanically. So you have an overlap on all kinds of different conditions in the battery, and we let it fail because we really want to understand what is wrong with our product and how could we optimize the design on our formulations or even on the battery design. Yeah? So that's how we tackle that. And then to coming to the last point here is, I mentioned efficient processing of our product is a big topic for us. So we also want to see how our materials perform in a production. So that's why we developed all kinds of different processes already. So gap filler is not new for us. We do this since 20 years, but gap filler in a battery had been new. So we worked with Atlas Copco, for example, to develop a process on having high throughput. We developed a process with our key technology partner to inject a gap filler for an OEM in Germany. We also tweaked certain technologies here, which are for applied sound dampening materials, and made it a two-component systematic for lid coatings. Yeah? So it's a main aim for us to enable already process technology and know-how to our customers before we even launch the product. Yeah? And to tackle that as well, we have a battery lab engineering center. So everything around the battery you see and do on applying different materials and even testing the materials, fast charging, temperature shocks, whatever we could do in-house. So we are not burning batteries, as mentioned, we're dealing with, but we testing our batteries and we assemble the batteries. So we could do everything on our own with the customers and testing all kind of materials. Yeah? We also simulating the behavior of the materials in our batteries to optimize design with our customers. Yeah? So that's how Henkel changed their scope over the last years to simply make sure that we always a front runner in this market, yeah? And not running after specifications, so really being more proactive and help our customers. So with that, right on time, I'm ready. Thank you for the attention. And as said, we have a booth. I'm there personally. Come by and happy to take your questions. Thank you very much.
Thank you, Mr. Xu, for enlightening us with the knowledge and with the information. May I please request more of your time, Mr. Xu? Can you please come to the dais so that I can present a small token of appreciation on behalf of Informa Markets India?